A transducer, chapter 8 in the previous edition, chapter 15, 8 and 15 in the new edition. So a transducer, a device that converts energy from one form to another. Microphones, actuators, loudspeakers, thermometers, antennas, photo cells, LED, light bulbs, windmills, and electronic and electronic sensors. So this is one of those things where electrical sensors are thermistors, but are transducers, but transducers don't have to be sensors, right? You understand what we're saying? It's like a Ford is a car, but a car don't have to be a Ford, right? You understand that? So the book calls them transducers, and that's kind of right, but we need to really understand what a transistor is. We're going to look at thermistors, photoresistors, Hall effect, ultrasonic, piezoelectric, and then I think we're also going to look at photoelectric too, okay? So a thermistor is a device that varies its resistance with temperature. And these comes in all shapes and sizes. And basically, they depend. Let me make sure this is a thermistor. So this wasn't the one I expected. So this is a typical thermistor. And I've got my ohm meter up here. And I think we can go down one more scale. And right now it's measuring 11.4 k ohms. And I'm just going to use myself. I'm not going to touch the leads, because if I touch the leads, the meter would measure me, right? I'm just going to touch this. And what starts to happen? Yeah, I need to probably get a soldering iron. It's probably better to see. And this is just me, right? 98.6. Notice what does it start doing? Resistance starts dropping. And then when I let it go, what happens to the resistance? So it's going up. So this is what we call a negative temperature coefficient. Let's look at that. We can get it in different ways. Wherever my PowerPoint's at. Right here. So a negative temperature coefficient, this resistance varies opposite of the temperature. So that means if the temperature goes up, the resistance goes down, right? A PTC, or a positive temperature coefficient thermistor, means it would vary in the same direction. As the temperature goes up, the resistance would go up. The predominant, of course, is the ETC. Predominant that you'll find out there. So the problem with the thermistor is the thermistor is nonlinear. First of all, it varies its resistance with temperature. But electronics don't look for resistance. Electronics looks for one of two things. It looks for a varying in voltage, right, or which causes a variation in current. So how am I going to take something that has a resistance that varies, and turn it into a voltage, which would turn it into a current? Well, Ohm's law's got something to do with it, but what type of circuit would it be? It's a very complicated circuit. So what I do is I got two options. I'm just going to put it in series with a resistor, right? You understand? So Kirchhoff's voltage law says the sum of the voltage drops have to be equal to the applied voltage. Then we also have the law of distribution, which means, which says the biggest resistor drops the biggest voltage, right? You understand that? So what happens on this one? What would happen to the output voltage if the temperature goes up So if the temperature goes up, if it's a negative temperature coefficient, which is what's being shown here, if the temperature goes up, this resistance goes down, this resistance stays the same. What would happen to the output voltage? Would it go up or would it go down? This is the kind of question y'all should answer, just like this. What are you thinking? Well, voltage don't move, right? But we know that the I is equal to what? I is equal to V over R. This is not changing. So if this resistance goes down, then my total resistance is going down, which means my total current goes what? Up. Which causes this resistor down here this is going to cause this resistor to drop less voltage because this resistance is going down. This resistor is going to drop more voltage. Right? You understand? That makes sense? Okay. So that means my output voltage would go up. If I want my output voltage to go down for some reason, I would just put my fixed resistor on the top, and then I would put my thermistor on the bottom. Usually they'll put a T in there for thermistor. And now I take my output voltage right here. Now when this resistance goes down, it's going to drop less voltage. This guy here is going to drop more, but I'm taking it across the thermistor. So it all depends on what you want. Do you want your voltage to go down when your temperature goes up, or do you want your voltage to go up when the temperature goes down? And this is why one reason an NTC negative temperature coefficient would work in both situations, because it depends on which direction where I put the thermistor at, right? You understand? Either the top of the fixed resistor or the bottom of the fixed resistor. The problem we have is thermistors. So this is ohms of the thermistor. This is temperature. This is typical. This would be for a certain thermistor. So normally when you buy a thermistor and you look at the data sheets, they'll give you R over several sections, which means you could generate the curve if you wanted to. That makes sense. So thermistors over its entire range it's a very poor temperature system. But what we do is we use it over a limited range. So notice right in this range right here, it's pretty linear, right? You understand? So this is where we use it. So they're used all the time in digital thermostats. I got a digital thermostat somewhere right here. This is one I got out of my house before I upgraded. So this was so this is a digital thermometer that replaces the old bimetallic strip that used to come out. Most houses, if you buy a new house, they're definitely going to come with a digital thermometer in there. Thermostat, excuse me. But notice it's got all these vanes in the back, and I flip it over, and what's this right here? A little white, that's the thermistor. Well, how far does your temperature vary in your house? I mean, it's very little, right? You understand? Maybe between 60 degrees and maybe 80 degrees, so that's only a 20-degree difference. So a thermistor would work great in that situation, but we would never use a thermistor over its entire range, right? So I've got one now that's got presets on it, so you can put 4 different temperatures during the day. So you can, like, if you and your significant other, somebody lives you works during the day, you could change your temperature so your heat's not running, right, and save a bunch of money. Also, you got 2 when you flip it on cold or HVAC, you got 4 temperatures for that too. Then you can set it up for the weekend, so you got weekdays and weekends. But I still have to flip mine between air conditioning and heat. They have them out now where you can just set one temperature And it'll automatically switch on heat or automatically switch on air conditioning depending on what you want. But these guys are pretty neat, but we have to generate that voltage, we have to put them in series with at least one resistor, right? Everybody okay? So we could do that. I've got a 10K resistor, so I'll come over here real fast and just set up the circuit. Won't take very long. Pulled it out. And so all I did was put a resistor in series with it, right? Got it in the same vertical line. Some of y'all are still having problems with that. And we'll put the positive on the top. And where did my other lead go? And we're going to put it across the 5-volt supply. So that way I won't have to adjust it. Put my common down at the bottom. And then I'll set my meters up. Set my meter up to measure what? Volts. Probably 4 volts would be okay. Okay. So what I'm gonna do is this is all the way across. So I'm gonna turn it on. My meter should go up 5 volts, right? And then what I want to do now is put it across my resistor. So we're measuring 2.34 volts. And now when I come up and heat this up, my voltage is going what? Up, because I've got my resistor at the bottom. And of course, if I take it off, my voltage should go back up. So now we've taken something that resistance varies with what? With temperature, and then we're outputting the voltage that's relative to that. That makes sense? Everybody okay? Yeah, the resistor's on the bottom. Here's my common. Okay. So this means if I was to swap it around, just by swapping my power supply around, then the voltage would go down. So if we put the resistor on the top, and my thermistor on the bottom, and it's a negative temperature coefficient, then my voltage would do what? Would go down.
So the resistor on the bottom is taking all versus
it's not, what do you mean by taking all of it?
take the drop.
Well, the voltage across it is going up. It's not taking all of it. It's taking this portion depending on the laws that we understand electronics, right? If I've got 2 resistors in a series circuit, one of them never takes all of it. It's proportional to the resistors, right? You understand? But what we have here is we have a resistor that's what? That's dynamic, which means what? It's changing with temperature. But still, it doesn't do away with the laws that we know that says the total voltage in the Ohm's law that says I is equal to V over R, right? So if this resistor goes down, then my total resistance goes down. If my total resistance goes down, my total current does what? Goes up. Now this goes down, which means it's going to drop less than the 2 volts. This is going to stop dropping more than what it was dropping before, right? You understand that? But if I swap them around, then I'll get a voltage that goes down with changing temperature. Here we get a voltage that goes up with changing temperature just by the what? The relationship of the 2 resistors. But the problem is I have no reference for that voltage. That voltage right now means nothing. All I know is that the temperature goes up, right? You understand? Now the voltage goes up. If the temperature goes down, the voltage goes down. But what does that have to do with temperature unless we can establish a what? A reference which says, okay, this voltage equals to this temperature. Now if I can know this voltage equals to this temperature, then what? So Celsius is a real good scale. So I would like that thermistor, if it's at freezing, to give me a voltage of 0, but it'll never do it, right? You understand, because it's always got an R. So let's just jump ahead to this slide right here. So we have something we call a Wheatstone bridge. You played around with this a little bit in DC, but this is where we use Wheatstone bridge right here. Wheatstone bridges allows us to take a a device, a sensor, whose resistance changes with what it measures and set a reference point. Right? You understand? So how does the Wheatstone Bridge work? Does anybody know? So if I was to come over here and I was to make this right here, let's say we make this a 1K, and we'll make all of them the same thing. Let's make this a 1K and a 1K and a 1K. What would I measure if I put my meter right there? And let's say we've got 10 volts over here. It measures 0. Why? So it's balanced, but why? Because I have plus 5 volts on that side and I have plus 5 volts on this side. What does my meter measure? It measures the difference of potential. What's the difference between plus 5 and plus 5? 0. So that means if we have what we call a balanced bridge and I measure across that center, it measures 0. If it's not balanced, it's going to have a voltage across there, right? If we could figure out the voltage. So if I came over here, I had plus 3 volts on that side, and then I had plus 5 volts on that side, what would my meter measure? It measured 2 volts. Right? So what would happen if I come over here, and I'm going to draw this so it looks a little better. Unfortunately, a lot of times they draw it like that. Well, we're going to draw it just like we draw the bridge rectifier. I'm going to draw it as a series parallel circuit because that's exactly what it is. So down here we'll put our common, and then up here we're going to tie this together, and we're going to come up here. This is where we're going to put our plus 10. And then what I'm going to do is this is where I'm going to take my output right here. So what we'll do now is we'll put a meter. But that could be the input to anything, right? You understand that? And of course this is going to be a voltmeter. So if this was a 1K and this was a 2K, and then this right here was a 10K, and this right here was a 20K, what would my meter measure? It's going to measure 0. Why? Because the ratio, the sides are the same. We could do the math. So I could come over here and say, okay, this 2K, it's going to drop. So we'll call this, let's call this R1, R2, R3, and R4. Since this is our common, this is what we're going to reference it to. So we're going to reference it to the 20K and the 2K. So VR2 would be equal to 2 over 3 times 10 volts. So what would VR2 be? Y'all know what that formula is? That's what we call the voltage divider formula. It's so dang neat because we can calculate voltage drops without calculating current. But we can calculate voltage drops with one formula. So what's my voltage going to be? Across VR2. 6.6. Huh? 2 divided by 3 times 10, right? 6.6 volts. Okay, so let's do it over here. So VR4, which is the one that's on ground, would equal to 10K over 20K. K is going to cancel. 0 is going to cancel. I mean over 30K, I'm sorry. What do we end up with? Sorry guys, hold on. I'm getting away from myself. So this is going to be equal to 10K, I'm sorry, keep doing doing this. They'll take care of me. What are those warnings? It's going to be equal to 20K. This is the one we want to find the voltage across, divided by RT, which is going to be 30K. And we're going to multiply that times 10. Well, right off the bat, I know what's going to cancel. I got K on the K is going to cancel. 0 is going to cancel. You notice we end up with 2/3 again. So VR4 is still going to be what? 6.6 volts. So if the ratio of these two resistors match the ratio of those two resistors in the same order, then we have what we call a balanced bridge. But what if this right here is variable, and what if this right here is variable? So here's my thermistor right here. Here's a resistor over here that I can control. The maximum output I get out of my thermistor is 20K. And it's going to drop down from there. All right. So what can I do now? Well, I can take my thermistor and put it in a glass of ice water and adjust it till it measures what? 0. Now I've got a reference. Right? You understand? And then I can put it in boiling water, which is 100 degrees Celsius. And then I can say, okay, that's equal to 100 degrees Celsius. And now it means something, right? You understand? So this, when we get into sensors that varies their resistance with temperature, you're going to see Wheatstone bridges all over the place. Because it gives us the ability to set a what? Set a reference. And once I set a reference, then that voltage means something, right? You understand? So this is the power of the Wheatstone bridge. I think back in DC, all you look and see is when it's balanced and when it's unbalanced. But this is what we use them for, right here. This is it. And we've got a lot of devices that change their resistance with what they measure. So the next device that changes its resistance with what it measures, it's called a photoresistor. A lot of people call this a photocell. So here you go. I can look at these. Now the size of these things would determine how much current they can handle. It's just like the size of the thermistor. So if we was to look at the data sheet on that thermistor, it would give us the maximum amount of power it could dissipate. If you ever let it try to do work that required more power, then that's going to cause a problem, right? You understand? So this is a semiconductor too. A thermistor is a semiconductor, and this is a semiconductor. But what they're doing is they're using when the light hits that semiconductor, it changes its resistance. So here's my photocell right here. Sorry it's glaring, guys. But y'all are looking at it. And I'm going to come over here and find my meter again, which is green and white. And I'm going to come over here and put it across this. I'm going to go back to ohms. So this guy's got low resistance, 564 ohms, right? And I'm just going to come over here and start blocking the light. And what do you notice happen? Yeah, so on photoresistors, the resistance goes up when the light goes down, right? So these guys operate in the opposite direction. Of course, this is still varying its watt, still varying its resistance with light. So if I didn't need it as a reference, if I didn't need to measure the amount of light, then I could come over here and just put it in series with a resistor, right? You then put a voltage across it. And depending on what I want it to do, I just broke one of the cardinal rules of meters, by the way. And we'll measure across the resistor. Okay. And then, of course, so here the voltage drop across my thermistor is doing what? I'm sorry. Well, my photoresistor. This is not photocell is the commercial name. The technical name is a photoresistor, which is what we'll use here. And of course, it depends on where I take my reference. If I go across the photoresistor, then the voltage will go up, right? So all I did is just change where I took my reference from. So here's my reference from. I can take it anywhere I want to, right? So here I'm taking my reference across my resistor. So if the resistance of the photoresistor goes up, then the voltage drop across the what? The resistor is going to go down. I'm covering that real good, right? If I take my output across my photoresistor, then that means now it's going to go what? It's going to go up, right? So it all depends on what your system needs. And this is also true with the thermistor. So if you take it across the sensor, it'll go one direction. If you take it across the resistor, it'll go over the other. If you put it in a Wheatstone bridge, and what's nice about a Wheatstone bridge is the Wheatstone bridge, where's my PowerPoint? Here. What's nice about a Wheatstone bridge is that a Wheatstone bridge would actually go negative. So we said I could put it in a glass of water, ice water, and set 0. Well, what happens if it goes to, 5 degrees below, minus 5 degrees? Well, my voltage would go minus, right? You understand? But it would still have the same ratio that we figured out before. So what's nice about a Wheatstone bridge, not only does it give you a positive indication from your reference, it also can give you a what? A negative from it, because what happens is the ratio on the other side changes now, right? You don't understand that. So you're going to run it in sensors. You'll run into Wheatstone bridges, especially analog sensors that vary their output basically in an infinite number of combinations. So these are photoresistors, and what's the commercial name? Photocells. Where do we run into these things at? Used to, when I was a kid, they started lighting parking lots. They used old timers, just old timers. And so, they would set what time they wanted the lights in the parking lot to come on, and then they'd set what times they wanted the lights in the parking lot to go off. But what's the problem? Well, summer and winter. So you'd see people that wouldn't go in, so they'd have to reset their timers all the time if they wanted it to come on at dusk and come on at the first light. Huh?
You got that playing all young, and the light came on, you knew it was time to go now.
Because why? Because they came on it. But now they use what? Now just about all the lights, even around here, use a photoresistor. And they're pointing up at the sky. And so now we don't have to do a timer anymore, because when it does, or a certain darkness, it does what? It'll turn the lights on, and at a certain brightness, it'll turn the lights off, right? So even now, if you got a bad thunderstorm that comes on, I've got a street light on the pole right out by my house. And I've seen it come on during the daylight. It's just that it's set to come on when it gets so dark out there, right? So it's pretty neat. They used to use them. The problem we have with these photoresistors is they're not extremely fast. So we don't use them to sense the light on our flashes anymore, because your flash is at a heartbeat. So we got to come up with something that's a heck of a lot faster, right? If we're going to sense the light of a flash, so our flash doesn't come on too bright, So a lot of your flashes now are very intelligent. Used to, we would aim them different ways to try to keep red eye and all that other kind of stuff. But our flashes now actually have the ability to do a lot of stuff for us on our cameras. They don't use these guys. The biggest disadvantage is these guys don't respond real fast. But we use them for sunlight all the time. Why? Because sunlight doesn't respond real fast, right? And we can probably even see this if we come over here and cover it up. See there? So what does it do? It takes a little time to do what? To respond. So these guys are not extremely fast, but we do have sensors that we'll get into the photoelectric sensors that are really, really fast. These guys are cheap. Photovoltaic cells. Commercial name is what? Solar cell. This is the symbol for a photovoltaic cell, so it's a symbol of a battery cell with the lights coming into it. So each cell is going to put out so much voltage at so much current, and then you can hook them in series to raise the voltage, right? Or you can hook them in parallel. So sources in series, what do we get when we hook sources in series? More voltage. What do we get when we hook them in parallel? More current. Okay, y'all understand that? So this is what they do. They hook them in series to get the voltage they need, then they hook them in parallel to get the current they need. So this is why you'll see these solar panels. They're made up of a lot of individual little solar cells. And they look pretty similar to this. If y'all have ever looked at one real close. So we have the semiconductor that we expose to light, so it's got some type of glass surface or a clear epoxy surface. And then we'll have wires in here that we either connect them in series or connect them to parallel. And then on this one we have a what? A plus minus output. That makes sense? So what's nice about these guys? What would be what would be the advantage of these guys over this guy right here? Well, this has to be powered. This don't. This generates power. This guy has to be powered, right? So what we would have to do on this, if my sensor is out there, I would have to have the Wheatstone bridge and everything out there, right? I would have to run power out to the sensor, right? You understand that? So that means I'm gonna have at least 4 wires going out to my sensor. This guy right here, I'd have how many? 2. Because this guy doesn't have to be what? Powered. This guy would have to have a power supply. This guy generates his own power. And the amount of voltage we get out of it, or the amount of current, but it's going to be voltage too to get a current right, would be proportional to the what? To the amount of light that strikes it. So we'll come over here. I got my meter on volts, and I'm gonna come over here and put it across my solar cell. Now I got mine backwards, the meter backwards. Right now it's picking up enough to get me out about 200 millivolts. Oops. I come over and cover it up. The voltage does what? Uncover it, the voltage goes up. So we could use this as a sensor to sense what? The intensity of light, which is what a photoresistor does. the big advantage of, and of course we could use it for a power source too. We see these guys all over the place. It's a lot of states, especially California, have solar cell farms to actually capture light. Now these guys, plus and minus, they put out DC. So if I'm gonna feed them into the power grid, somehow I'm gonna have to take DC and convert it into what? AC. And this is where inverters and stuff like that come into play, electronic circuits that do that for us. So if I need more voltage, I would just take the plus output and feed it into the minus and one beside it, right? And just hook them in series 80. And then if I needed more current, I would hook the cells in one parallel. So this would be one cell right here. So most solar panels, even now going out the interstate, we see lit signs out in the boondocks, right? Like between Montgomery and Enterprise down that way. There's nothing down there, but you'll see lit street signs. But if you look on the side, what do you see? You see a gray box over there, and you'll see a photovoltaic cell pointing up to the sky. So they charge batteries during the day, right? You understand? And at night they use it to run the light. They have a competition every year where they have a car race, and the cars are all what? Solar powered. So they run them during the day. I think it set the world's record of a drone that was flying around up above the clouds. That was, I don't know if it's still up there or not, but it flew but it was all solar powered because now it's above the clouds, right? And it always had a power source. So these guys are really, really neat. And these are called, generically they call what? Or commercially solar cells, photovoltaic cells. These are the technical names. There you go, Damon. You're the gopher. So that's the correct symbol, right? Everybody okay? Hall effect. Hall effect is an integrated circuit. So one thing a Hall effect has to be, it has to be powered. But what it does is it varies a voltage proportional to the strength of a watt. Magnetic field. You understand that? Now, I don't know if this book says it, so let's look this up in our textbook. See exactly what it says. What page? 70 in the old text. Where's it at in the new text? It's hard to say. They look like they are. They might be hooked in series. I think they rated it. We had and of course we have. I don't know where it's at, guys. I need to find it. I think it's in A building. But over in 250, when that used to be one of our classrooms, we had a solar panel that was donated to us by, I can't remember, Bell South or Alabama Power. And we hooked an LED up to it. But the fluorescent lights put out so little light, we hooked the LEDs directly to it. But we didn't put a resistor in series with it. Nancy took it outside one day and blew the LEDs just like that. I don't know what those would put out. But yeah, because she got out under Mr. Sun. These guys fake us out, right? They don't put out the light that you think they put out. This is why when you take pictures under fluorescent lights, usually it turns out yellow. Because your camera sees the true light, and we see a fake light. This is why things take on different colors. I don't know if you ever noticed that, but there was a picture where they had one color and they had a fluorescent on one side and an incandescent on the other, and they broke it, and the shirts were actually different colors. Our eyes, our brain is an amazing thing. it compensates for things like this. So these guys don't put out a lot of light, true light. They put out about what we think is a lot of light. Because these guys are turning off and on 120 times a second. Because they flash, they're flashing, literally flashing, but they're doing it at a rate that we can't see, and we blend them together because of the persistence of our comet. So what does it say, the two types of Hall effects? Does it tell us? They don't. But we do have two types. One of them we call latching. And the other one we call it a linear. So a latching, what it does, it's got latching circuits in it. So one polarity, one field will cause the output to turn on, and then you can take the field away and it would stay on there forever. You could bring the same field in there like the north and it would stay on. For it to turn off, you have to give it the opposite field. So north might turn it on and it would latch it, and south would do what? Would turn it off. The linear type is what they say here. It literally varies its output voltage depending on the strength of the field. So we could use that to measure the strength of a magnetic field. So they have to be powered up. They're usually built into things, but they're going to have 3 terminals. They have to be powered up. One of them's going to be for your watt, your power. One of them's going to be for your common. And this is what's going to vary right here, this signal output, relative to your common. So that wherever I got this, they called it ground. And like I said, ground is one of the most misused terms used in electricity. That pin does not have to be grounded. It could be a circuit common, right? You understand that? A big difference. So what is a circuit common? What's the difference between a ground and a circuit common? And you need to know. Yeah, ground is earth ground. It means it's reference to earth ground, right? And then a common is not reference to earth ground. It's just the return conductor in a DC circuit, or it's your common conductor in an AC circuit. And we found out the other day that what our trainers call ground is not ground, it's a common. So this is one of the misused terms in the field. And just because you use ground, that's okay, but it's imperative that you understand the difference between a common and a ground. So we have to power these things up. So we have 2 types, and we're fixing to take a break. Well, they're not designed to handle a lot of current. So, I was right where I wanted to be. And I just went right past, slow down, Rick. There we go. So this is the Hall effect right here that I'm fixing to wire up. This is a latching Hall effect. So this guy will respond to one polarity, right? Then we have a linear Hall effect, if I can figure out which one it is. And this should give us an output voltage that's proportional to the magnetic field. What's nice about this is that the problem we have meters called clamp-on ammeters. You know what I'm talking about? And what do they do for us? We have 2 types now. We have a clamp-on, what they call a fork meter, but basically they do the same thing. So what does a clamp-on ammeter do? What does it do? What does it measure? Not directly. This is a big thing people don't understand. It measures it indirectly. Good gracious. That was interesting. So these are all clamp-on ammeters. I think I got one. Huh? Yes. So what does it measure? But we have the ability. So what's required to induce an EMF magnetically? I have a magnetic field. What's the thing? What's the next thing we need? Huh? That's the amount. We're figuring out what we need to start off with. So what's the next thing we need beside a magnetic field? I ought to put that on every test that I give. Now, what determines the amount is the strength of the magnetic field. The next thing is the number of conductor loops. And the third thing is the speed of the motion. And so this is what a transformer operates off, right? This is what an induction motor operates off of. Most of your AC motors are what we call induction motors. So we got to have motion. So AC, DC don't give us what? Motion. But what gives us motion? AC gives us. Okay. What determines the strength of the magnetic field? If I put so anytime I put current flow through a conductor, it creates a magnetic field. What determines the strength of that magnetic field? Starts with C. How much current we put through the conductor. So AC, I got to change it. I got motion out of AC, right? You understand. The strength of the magnetic field is determined by the amount of current. So if somehow I can measure the strength of that field, then I can know what the current would be. And that's what a clamp-on ammeter does. It's nothing but the secondary of a transformer. They're called CTs, current transformers. We run a wire through it, and then we measure the strength of the field. And these are used in industry all the time to measure current without breaking the circuit, right? But what's the problem is this has got to be what? It's got to be AC. So clamp-on ammeters will not measure DC in the clamp. They'll measure AC in the clamp. Most of them have terminals you can put in to measure DC current, but if you measure DC current, what do you got to do? You're using a true ammeter, which means you got to do what? You got to break the circuit and put it in series. Y'all understand that? But what does a Hall effect do? A Hall effect measures the strength of a DC field. So now I can come out with a more expensive clamp-on ammeter, right? You understand, that uses Hall effect to measure DC. So we have clamp-on ammeters, guys, that will measure both DC current and AC current in the clamp. Well, how does it measure DC? Well, it uses a watt. It uses a linear Hall effect. And these cost a pretty good deal of money, DC and AC clamp-on ammeters. But the problem is they're rated at extremely high current. So if you ever look at a clamp-on ammeter, usually the lowest current it'll measure reliably is like 40 amps, and then it might go up to 400 amps. So these guys are really good for measuring what? High current, like motors. You see a lot of electricians wire them. Now there is a trick you can use. You can take the clamp and then you can loop the wire. If you loop the wire twice, then your meter is going to measure twice what it's supposed to do. So you can make it measure smaller currents, right? You understand? So now you can measure 20 amps reliably by looping it what? But if you loop it twice, if it says 40, it's actually what? 20. If you loop it 3 times, then, so that's a trick that you can measure lower currents with a clamp-on ammeter just by doing what? Looping the conductor in the same direction, by the way. Okay, guys, I'll take a break and then I'll wire up a. So I didn't have time to wire the other one up. This is a latching effect. And this is a HI 300, which is a switch, so it's a latching one. It says I can operate it on voltage between 2.4 volts and 26 volts, which is pretty good, right? On-chip Hall effect sensor. Another thing that we were interested in was the pin out. So pin 1 is where I put my positive supply, pin 2 is where I put my ground, and pin 3 would be my signal out. We're okay? And normally on these devices, you hold it up toward the front, and the pins are numbered from left to right. We're okay? This is the actual basic circuitry. So we hadn't talked about this before. This is the actual output. This is the Hall effect over here. Kind of voltage regulator in. We don't know. It might be a Zener diode, right? You understand? Which allows us to operate it over that big range, right? You understand? So no matter what so it probably operates around 2 volts. So 2.6 up to 26 volts, it still sees the same thing. This is going to turn on a what we call a NPN transistor. Which means it's syncing. Does that make sense? Have we talked about that before? Yes? No? When we get into digital sensors, we have 2 ways we can run digital sensors. And basically, syncing and sourcing only deals with DC. It has nothing to do with AC. And let me go back to my Wheatstone Bridge where I have a blank sheet. So in electrical controls, we come over here and we, have y'all had motor controls? Okay. Motor controls is basically we come up here and we have two circuits. Generically we call this L1 and L2, but that's my power. L2 is considered the common, and then L1 is considered to be what we'll just call the hot. And we connect circuits between these two rails. So I could come over here and let's say this is my sensor. This is my latching sensor. So what I'll do is I'll just draw it as a contact. Well, let's don't do it that way because some of y'all don't know what that is either. So let's draw it as a switch that's being controlled by my magnetic field. And then I'll come over here and I'm going to put my load right there. So that's a basic circuit, right? You understand? So this is my sensor right here. Now what do we have the ability to do? Well, this is the way I would hook my circuit up. So all my sensors would be over on this side. They would be on the L1 side. And then my loads would be on the L2 side. And how many things could I put? A lot, yeah. Okay. So, what is common? Well, common, we call this common. Let's just don't call it common. Over here on my sensors, this is my common because it's a wire that's connected to all of them, right? You understand? Over here on this side, this is my load common because all my loads are connected to this side. That makes sense. So common is just a common connection spot, right? You understand? So I could come up here and I could make this plus and I could make this minus, and that's DC. Or I could do what? I could make that minus and I could make that plus. Does that make sense? Yes or no? So this came up from DC. From digital. When we use a negative common in digital, we refer to that as syncing. When we use a positive, so a positive we call sourcing, and then a negative we call syncing. So if I come over here and make this positive, and then I make this negative, then my sensors are going to be what? My sensors are going to be syncing, right? You understand? If I make this positive, then my sensors are going to be sourcing. Does that make sense? So, but when you look at the data sheets on sensors, they're either called PNP or they're called NPN. An NPN sensor is a syncing sensor, which it means it provides the minus, so I have to provide the what? The plus to get current flow. And a PNP sensor is going to be a sourcing sensor. So the sensor is going to require, it's going to provide the plus, right? You understand? And I have to provide the what? The minus. That makes sense. So when I look at this diagram right here, and this is the diagram, this is an NPN transistor. So that means it's what? It's syncing. Okay. So that means if I hook a load up to this thing, which I'm using the LED, I'm trying to get to my markers, guys. Oh, this is the data sheet. I'm sorry. Let me see. Shift Alt D. So that means if it provides the ground, then my load is going to have to be connected to what? To plus, and this is where my load's going to have to be. I don't know how I'm doing that, but this is where my load comes. So a sinking resistor, a sinking sensor would require a sourcing load, right? Does that make sense? That make sense? So what I have connected up here is I have a resistor, and then something that we hadn't got to yet, which we're going to talk about, we have a light emitting diode. Huh? A light emitting diode. Most people call them LEDs. Have you heard that term before? So it's a light emitting diode. Okay. And we put it in there forward bias to make it emit light. So I'm going to have to put a power supply up here, but what's nice about the sensor don't care. So I'm just going to use plus 5 volts. And then we'll talk about how to size the resistor. And then inside my Hall effect, now I have a circuit. So when I turn this guy here on, the LED comes on. So this is a sinking sensor. So if you have a sinking sensor, it means you got to provide the source, right? So your load's got to be hooked to positive. If you have a sourcing sensor, then you got to supply the water, the negative. Does that make sense? So this is a sinking sensor. So when I look at my light emitting diode that I'm going to turn on and turn off with my magnetic field, as soon as I can get my camera to come up. Oh, I know what I need to do. I need to escape and get out of this. So here's my LED, my light emitting diode. Here's my positive right here, going to the top of the resistor, and then it's in series with my LED, and then this is hooked up to pin 3, right, which provides the negative. So my sensor's providing the negative, I've got to provide the what? The positive. And it's powered up, the LED is off. This is a switching sensor or a latching sensor. So when I bring one polarity into it, my LED did what? Now I've got it up here in my hand. How long is it going to stay on? Until I turn it off, or I'm going to hit it again. Oh my goodness, it's not turning off. It's latched. We got to give it the opposite field, right? You understand? So I'm going to take my magnet, I'm going to spin it around and bring it in the opposite direction, and then it turns off. So one polarity turns it on, or the other polarity turns it off. What's nice about a circle is that the polarity shifts. So I can literally come up here and do this. See that? So we use a lot of Hall effects over there on our cylinders to tell when they're extended and when they're retracted, and that's the way it works. So it's seeing this magnetic field when it hits a certain spot, right? You understand? And then when it goes away from it, it does what? Sorry, should see the other field. So right now it's seeing one field, and then when it moves away from it, it turns it off. So this latching Hall effect is pretty cool because one field does what? Turns it on. The other field does what? Turns it off. Very simple circuit. I just put my load in series with my ground. Now what we need to know is we need to know how much current that output can handle, right? And where would we find that at? Find it in data sheet. So here's my electrical characteristics right here. Oops. So here it says my output can handle what? So output can handle supply current, current. I don't see it in there. Supply voltage, output saturation voltage, output leakage current, supply current. This is at 10 volts. It's 2.8. See if it's down here. Oh, there it is right there. Output on current, maximum what? 25 milliamp. So I could run a 25 milliamp load directly off this thing. If I needed more current than that, then I'd have to use something that gives us a current gain, we're going to get to before the end of this semester. I'm running an LED. An LED typically pulls about 15 milliamps. I'm running it at 10. So we'll show y'all later on how to calculate the size of that series drop-in resistor. Because it's a diode, guys, and once a diode is forward biased, it acts like a closed switch. So you're going to have to protect that thing with a resistor, right? So that resistor determines how much current flow you get through that LED. And we'll show you how to do it. It's really, really simple once we get into LEDs. That's a latching Hall effect. And what I'll do during the next break is I'll hook up the linear Hall effect. So you have any questions on that? Pretty neat. Okay, on sinking and sourcing. So this would be a sinking sensor. It does not metal, but we can make it appear to measure metal. Notice what they're doing here. They have a magnet that's sending the magnetic field through the watt, through the Hall effect, and then they have a metal tab that's spinning around. Well, every time that metal tab spins around, it's going to change the magnetic field, right? And the Hall effect will give us another output. So we can make the Hall effect appear to measure metal, to detect metals, but we're using it in combination with something else, right? You understand that? So no, what do they measure? What does Hall effects measure? Of a magnetic field. So this has got it's got a threshold built into it that determines when it switches. So you got to have such a certain strength magnetic field before it switches. If you put it above that, it's not going to do anything. If you put it below it, it just wouldn't do what? It just wouldn't switch. Ultrasonic sensors. Y'all seen these guys before? So ultrasonics is basically kind of like sonar. How does sonar work? Sound wave, right? And then what does it do? When it hits something, it bounces back. And depending on what material they shoot the wave through, how long it takes to reflect back would give them a direct indication of how far that object is away, right? Submarines used to use it all the time. They use it very seldom now because why? Because they give away your location, you know. Most of them use acoustics. They use the actual sounds being produced by the items themselves. Ultrasonics can be designed to sense what? Distance, movement, solids or liquids, speeds, directions. All it's got to do is be a surface that bounces back. If it absorbs it, then ultrasonics has problems. And that's what they're doing with a lot of our airplanes now, right? Giving them weird shapes, right? No flat surfaces, weird shapes. And they're coating them with an acoustic material that absorbs sound. Because radar works basically the same. Limited by the surface shape and density. So here's some examples of ultrasonics. We have basic small ultrasonic sensors. I get this every once in a while. What's that? You never seen it before? It's ultrasound, you know. It's ultrasonic. It's what it is. It's ultrasound. We use it all the time, you know. This is the way they look in our bodies all the time. I get it every once in a while when they check my leg out to see if I'm getting any blood spots, which is pretty neat. Women get it when they're pregnant, right? And they coat it with a gel, a coupling gel, you know, to get a really good indication. So we can use these guys to measure distance. We can use them to measure height. We can use them to measure motion, right? Things in motion. We got an ultrasonic sensor over here. These are usually what we call shielded sensors. Notice that the actual outside threads go all the way up to the sensing element itself. We have what we call unshielded, where the actual sensing element sticks out past the threads, and we'll look at that. You'll probably never see an ultrasonic sensor where they want to focus the waves. They don't want things to do what? They want the waves to spread out. You'd be surprised. These people are blatant. They carry a straight face. They'll go in there and they'll roll out. They'll come rolling that thing out. Nobody.
Hey, I think the man gonna know the whole right there. See, the lady said, I don't get paid no check by that.
I can understand that too. Okay, guys, y'all need another break? 2 minutes. Okay, I hooked up the linear sense Hall effect. It's a sourcing sensor. So here's my circuit. I'm sorry I got all the same color wires, guys, but so power comes in on pin 1. Should be right here. This goes up to 6 something volts. If I'm using 5 volts, that's okay. Pin number 2 is my common, and then pin 3 is my output. But unlike my other one here, I have my output. So here's my resistor. I'm using a 1K resistor. No, I'm not. But that's okay. I'm using a 330 ohm resistor. I should be using a 1K, but what would be a 1K? And so this is the orange, brown. So it's a 330 ohm. But I've got its other end connected to mine's. So this is a sourcing sensor, right? That makes sense. So here's my magnet, and this is a linear sensor. So I'm going to start bringing my magnet in toward it. Notice right off the bat, the voltage drop across my resistor or my load is going down. And the closer I get to it, which makes the magnetic field is getting stronger, right? So as the magnetic field is getting stronger, its output voltage goes down. Watch what I'm going to do. I'm going to change the polarity, and I'm going to start coming toward it again. And my output voltage goes up. Huh? It would be about the same depending on how I'm aligning the magnet. It should give us the same output voltage for both of us, the same delta, the same change for the same field, right? Does that make sense? But one polarity makes the output voltage goes up. One polarity makes the output voltage go down. Now, so this guy here is a source. It's a sourcing sensor. So I had to put my resistor in between it and common, right? You understand? Between it and negative, not common negative. So this is linear. This is the latching. This is linear. Now, the only thing difference is the electronics inside the sensor when they make it. They either make it. But these guys have to be powered up, right? You understand? So they're going to have at least 3 pins. 2 of them's for power and 1 of them's for signal, which is pretty common. We call them 3-wire sensors. So normally 3-wire sensors have to be what? They have to be powered. Are we okay? That makes sense? So let's go back to our PowerPoint. Okay. Here's the data sheet on my sensor. But it had the same pin out as the other. Okay, so piezo. What is piezo? Piezo. Yes. It's, okay, I don't see it. Did I spell it right? Yeah, okay, no, I didn't spell it right. No wonder. Yeah, I should have known that. You see that? Let me blow it up.
You know,
Which means to what? Can y'all see that? Squeeze or press. Now, piezo means squeeze or press, right? You understand? Piezo resistive means it changes its resistor if resistance if you do what? If you squeeze it. So these guys are used to measure pressure. Because if pressure, with pressure we can generate a force, right? Which would cause it to squeeze. So piezo resistive, these are pressure sensors. This is not in your textbook, by the way. This came out of another book. I couldn't find it. Is piezo resistive in your book? Piezoelectric, which is different than piezo resistive. So what would piezoelectric do?
Piezoelectric is transduced to operate based on the interaction between certain materials and electric.
We could read it, but let's just reason it out. Piezoelectric. With what? Pressure. This is the way, when I was smoking in our cigarette lighters, we used flint, right? So you spin around. I had Zippo. Still got my Zippo. But those guys are now hard to find. Zippo and actually, the butane fill that you fill up the lighter fluid you fill that up. Most of them now are piezoelectric. So what you do is you generate a pressure, you pop a piezoelectric crystal, and what does it do? It generates voltage arcs across there like your cigarette lighter. So that's piezoelectric. Yeah. No, not the one with the flint, the one that generates the arc, the one that snaps. So you push it down and you get it to a certain point, it goes pop, and then it shoots. Right? Those are piezoelectric. But we're not talking about piezoelectric, we're talking about piezo resistant. So this might not be in the textbook. And we use these a lot because they're solid state. There's no moving parts. So we got a pressure sensor over there on both manufacturing lines. One of them is digital, but we got an analog one over there too. The way they do it is that piezo or lit resistive, I don't know, but all we know is they're pressure sensors, right? Makes sense. Pressure is a very important thing to measure. And when you take the sensors class, we got several ways we can measure pressure, but this is solid state, so all we're looking at is the semiconductor sensor, the solid state sensor. What happened up in, what was it, outside of Boston? When all those houses caught on fire? You know what that was? Somehow they got too much pressure in the line. So something went wrong. Well, they should have a bunch of pressure sensors out there, right? Monitoring the pressure in those lines. Trying to do something about that. Yeah, I would like to be a lawyer up there right now. Tell them it's sued. So these are typical pressure sensors. They could be big, they could be little. They could be 3-wire sensors or 4-wire sensors. They could be digital or they could be analog. And they still have to be powered up, right? Everybody okay? That makes sense? So this is a typical pressure switch. got them on compressors. These are digital. These are probably operating on the bellows. Transducers, photoelectric. So this is up in chapter 15. I think it's still in chapter 8 inside the old group. LEDs, what does that stand for? Yeah, liquid crystal. We call them LCDs, liquid crystal. Right? Photodiodes, photoresistors, we've already looked at. Photovoltaic cells, we've already looked at. And we have these photoelectric sensors through the beam retroreflected and diffused. Are we okay? Need to understand a little bit about light. These are electromagnetic waves at extremely high frequencies. Light frequencies are 1 times 10 to the 14th or slightly over the 1 times 10 to the 15th. The visible light, these are the range of frequencies of visible light. 4.29 times 10 to the 14, 7.5 times 10 to the 14 hertz. And relative to rate FM. What does FM stand for? What? Forward modulation. If we're going to change a signal, what's the two things we could change? We change its frequency, or we could change its amplitude. So we have two types that's predominant, it's AM and FM. So what we have to have the ability to do is to transmit this through the air, and not only be able to transmit it, but be able to receive it, and also to be able to filter out what we don't want and only let what we want pass through. So the technique of putting a signal on another high frequency waveform, a higher frequency waveform, is called modulation. And so we have what we call a carrier. It carries the frequency, right? It carries the information. And then when we get into our radios, we strip the carrier off. Somehow we strip the carrier off and let the information come through. So the two primary ways is what? We can modulate the frequency, or we can modulate the amplitude. Originally, when they started broadcasting, they did the amplitude. But what they found out real fast is that electromagnetic interference changes the amplitude. So this is why AM is so noisy. AM hums all the time. Because 60 cycles all over the place. It's real hard for EMI to change the frequency. So this is why FM is so popular, because it's real hard for EMI to get. You know what EMI is, right? Electromagnetic interference. And it's all over the place. I mean, because if I put current through a wire, it generates a magnetic field. How many wires do we have in this building right now? So this electromagnetic interference is flying all over the place. And I'm a semiconductor. I'm a carbon-based life form, right? Somebody else put my soul code. Well, I was going to show y'all me. So I pick up electromagnetic interference. Make sure I'm plugged in back there. Oh, I have to be. My power supply. Is it plugged in? No. In the forward. Alright. Are the power supplies on? This is running. Okay, mine's on. Oh, okay, you got jerked out. Oh, Kenny, somebody power. Got 1,000. So guys, this is me. This is because this is caused by, so I'm a semiconductor, right? I got all these magnetic waves flying through me. The predominant one is what? 60 cycles. So what I'm going to do is I'm just going to come up here and touch the tip of this scope probe. Huh? 60 cycles, right? And there's a lot of garbage riding on top of it because we got all type of frequencies. So that's what that ghosting is all over the place because of all the other frequencies, right? Coming through the air. My body's doing what? Picking them up. So this is one way I check to see if my scope probe is hooked up or it's working, or if I got the right channel selected. I just do what? Just touch the tip. So that means if I've got all these electromagnetic waves out there and I've got a conductor and that electromagnetic waves go through that inductor, it can produce a what? It can produce an EMF into that. We call it, if it's undesirable, we call it EMI, electromagnetic what? Interference. So that's what EMI is. So FM won't pick up EMI because EMI don't want to change the frequency. EMI wants to change the what? The amplitude. And that's why FM, like I said, FM's always got a 60 cycle humming. Because we got 60 cycle all over the place. If y'all listen to AM lately, but you'll always hear what in the background? Right. 60 cycle, like transformers. Huh? I listen to radio all the time. Of course, now we have those satellite radios that, well, they're actually pay an annual fee. So you don't have to have commercials. Yeah. So, light, we don't have to worry about electromagnetic interference with light either, too, right? So this is why it's pretty popular. This is one advantage fiber optics has over copper wire. Is this immune to EMI? EMI cannot, it can induce a voltage, but it can't do what? It can't change light. And that's one big advantage of fiber over copper is that it's immune to noise. If you're immune to noise, it means you can start pumping the frequency up. So electromagnetic waves, everybody understands that. So, you know, these things are moving in waves. They have frequency and everything. We get up to the electromagnetic wave, getting up to a certain, so that's all the sun is doing is generating these big electromagnetic waves. And our human body interprets those waves as light, right? So we can actually see this, which is really, really cool. So here's our visible spectrum right here. And down below, by the way, usually in light is such high frequencies, 10 to the 14th. We're talking terahertz, right? Well, no, terahertz would be 16. So what we usually do is we know that waveforms, if they're equally spaced, then they're literally got a space between. It's like the ocean waves coming in, or somebody doing a road like that. And there's actually a space between those oscillations, right? And we can actually measure that, or we can calculate that. So usually light is given in what we call wavelengths. It uses abbreviation of lambda. If we're going to indicate that, so you'll see a lot of would say, and lambda is this guy right here. So 600 nanometers. So that would be the wavelength between the pulses, right, or the zero cross. 60 nanometers, 850 nanometers. These are the ones. By the way, these are the ones most widely used in fiber optics. 660, 8. These would be visible, right? You understand? When we get up to 1300, you couldn't see this anymore because it would be in the infrared or in the spectrum that we can't see. So, Gilbert, you got this. What runs at 660?
I remember talking about the 660 and 850.
What type of cables run at that frequency?
Fiber.
Multi-mode runs at the higher frequency. Single mode runs at the 13s, the 1310s, and 15. Very high frequencies are usually given in wavelengths instead of hertz. Every repetitive electromagnetic wave moving through a media has a length referred to as a wavelength. Wavelength is determined by the frequency of the wave relative to the speed of light, which is 3 times 10 to the 8 meters per second. So this is why wavelength is not given in inches, it's given in nanometers, right? You understand that? Relative to light, so that would be the speed of light. Big. So here's where you use your notation. Y'all don't have to do this, we're just talking. So this is the actual formula for wavelength. We multiply it by 10 to the 9th, and then we call it nanometers, right? You understand that? Are we okay? So y'all learn this if you're in fiber. Here's the wavelength. So we're dealing with frequencies in this range right here. So visible light, the more we move this way, the more it shades towards red. The more we move this way, the more it shades towards violet, right? Everybody understand that? We got all the colors in between. So everybody, hopefully y'all know this already, right? Engineering notation. When holes and electron combine at the junction of a forward bias diode, energy is released in the form of photons. Everybody okay there? Silicon and germanium release very few photons, and these semiconductors impede the release of photons. So silicon diodes and germanium ion diodes don't make good photons. If they do release photons, they're a wavelength that we couldn't see anyway. It would be so few that it would be so dim we couldn't see it anyway. Everybody okay? For this reason, LEDs are made with variations of doping gallium. Huh? No, it's a fault. So light energy, everybody okay? So this is what's happening when it forms that collapse when they hit. It releases a photon. Photons we can see if they're in the right visual length, right? Contrary to popular belief, the color of the lens of an LED does not determine the color of the color emitted by the LED. The lens only enhances the color that the LED emits. And of course, the color emitted is determined by what we dope the gallium with. Does that make sense? So gallium arsenide generates a light around 900 nanometers. Gallium arsenide phosphide hits about 660 nanometers. Gallium phosphate produces 560 nanometers, which is green. Gallium nitrogen would be 430 nanometers, which is blue. Gallium arsenide phosphate, gallium phosphate would be 635 nanometers, which is orange. And we can keep going. The problem is that for years we couldn't there was no such thing as a white LED. And why is that? Because white is not a single color. White is multiple colors. Y'all understand that? So I forgot his name. I need to look it up. But the guy that invented the white LED actually won a Nobel Prize in physics because they'd been trying so long. And you can still see them out there. We can get a bright blue. So a lot of your cheap flashlights and stuff are a bright blue because it's been so hard. But I really like blue. So here's our color spectrum right here, the different dopings. This is just nothing that you need to know. It's just that we can get all types of colors now with the techniques that they have. But look at they do it with multiple items. So they do multiple dopings to get what? To get different colors, and then now we can move to white. Now they got high intensity too. It took them a real long time to get these LEDs to handle a pretty good deal of current. So now we got high intensity LEDs lights. And eventually, guys, even automobiles are going to go to their main lights are going to be what? LEDs. We're moving that way. Guaranteed. Huh? Yeah. So this goes all the way to cool white, and super lime yellow, super lime green, high efficiency green, super pure green. We can get just about any light color now inside the visible light spectrum. All the way outside too, we still use a lot of infrared. We don't use a lot of ultraviolet because ultraviolet's dangerous, right? It wants to make things oscillate and makes things burn. But infrared is safe. So, most of our remote controls. So this guy right here is infrared. So you don't see it, but that's what it's doing. It's just flashing a light, right? You understand that? I don't know if this camera right here will pick it up or not. So this is the symbol for a light emitting diode. Most people leave the circle off. That's all the symbol of a diode. And then they'll put the two arrows pointing out from it at an angle. Exactly 45 degrees right now. So what happens is we forward bias these things, they light up, we reverse bias them, they turn off. If you exceed the breakover voltages, we burn them up. If you exceed the current flow through them, they're going to burn them up, right? You understand? So normally we're going to protect these guys with a resistor. But we'll learn later on when we get into transistors, we can come up with what we call current sources, which basically would give a certain current, and you won't see resistors in those circuits. We run into these guys all over the place. So these big old displays, there's nothing but a lot of high intensity ultraviolet light. I mean, not counting 7-segment displays. We call it 7-segment displays. These are nothing but LEDs arranged in 7 segments. Can y'all see that? And we can display what with these guys? We can display any number from 0 to 9. Very simple. We can get these common anode or common cathode. So here's some 7-segment. I don't know what these are. These, huh?
I can't remember it digitally, but I remember going over them those 7-segment displays. Wasn't it like lettered inside on like A, B, C, D?
No, we can do some letters, but they have what they call a star. It's got more than 7 segments. We can't do a lot with a 7-segment display. We can do some letters, but we can't do all of them. So we could like do an A, we could do a lowercase b, we could do an upper or lowercase c. Here goes then. Or we could just use multiple LEDs. I mean, this is pretty popular, especially on like 50 days, where they just have a bunch of LEDs and they just turn them on in whatever pattern they do. Now these guys can do anything, right? They can do anything. Or these 7-segment displays, these are very, very popular. So this is a 7-segment display. Now it's not LEDs, but it works on exactly the same principle. So we see 7 segments in here, and we can display. So these guys work really, really well with displaying numbers, right? You understand that? Display characters. We could do sort of a Y. We could do sort of a T. Can't do an X, right? Can't do an O because an O would be considered to be a 0. Normally if they do an O, they do just the bottom segments, the bottom 3 segments. By the way, these segments are given names. They start at the top. We call it segment A. Then we go clockwise. A, B, C, D, E, and then the F. And then the center one is called the G segment.
That's what I'm talking about.
Huh?
That's what I'm talking about. Segment.
Yeah, they're. But we have what they call star. They call them star. They might call them. That's what I call them. But they'll come in here and they'll have the primary segments. But in the center, it will be like this. They'll have like that, which gives a slant, so we can do other letters besides just numbers. But primarily, these guys are just 7-segment displays. They're used for numbers, where we don't have to do letters, right? Of course, a lot of things are moving to LCDs, which we'll talk about in a minute. But LCDs work exactly on the same principle. So that's an LCD, but it's a 7-segment display, right? You can actually see the break between the segments on this meter right here. So y'all run into 7-segment displays all over the place. Except these are what we call liquid crystal displays. And we'll look at those too to see how those work.
So I'm actually putting in your car. Now you got the speedometer. Would that be a 7-segment display?
It could, but if all it's doing is displaying information about your speedometer, if you got a digital thermometer, not thermometer, speedometer. But it might be LED, maybe not. A lot of time they'll use something that's a lot brighter. They used to use plasma a lot, plasma displays, but now they're probably using liquid crystal. But you get multiple colors out of liquid crystal. The problem with liquid crystal, though, is they have to be backlit. So an LED generates light. Liquid crystal don't generate light. All it does is block light. So that's why we have to backlight LCD displays. So here we're using the outside light reflecting off a background to block the light, right? You understand? Your screens either use fluorescent bulbs, or now they're moving to LEDs, and they call them LED displays, but they're not. They're LCD displays. They're just backlit by what? By LEDs. So when you hear LED displays, that they are not LEDs. They're actually LCD displays, backlit by what? By LEDs, which gives us an advantage because they'll put thousands of nice white LEDs back there, and if one of them goes out, you usually don't bother you. If they put one fluorescent bulb back there, if that fluorescent bulb goes out, it does what? It's no good. We got about 8 displays over there under the server that's bad because the fluorescent bulbs are went out
there. That's when they got the LCD TVs, you got the LED.
Well, they're LED TVs or LCD displays. They're LCDs, but they're backlit by LEDs. That's the only difference. So, but they call them that. So your old ones, and if you look at the difference in size, your fluorescent LCDs had to be big because they had to have what behind there? They had to have that fluorescent bulb. Your LEDs are going to be really, really thin now because why? Because they're backlit by LEDs. So this is an LCD screen. It's just that it's backlit by LEDs, and that's why they call them LED screens. But technically they're LCDs backlit by what? By LED. Does that make sense?
So the LEDs are real thin TVs.
Yeah. Because LEDs are small. I mean, they can make things extremely small. This is big. Here's the ones I call the star right here. I can't make it any bigger, but you can see these. And these guys, these are LEDs. They can do anything. They can do letters, numbers. They can't do descenders. You know what I mean by descenders? Go below the line. When dot matrix printers first came out, if they did a Y, a lowercase y, it was up. The Y was up with the other letters because they couldn't do descenders, but after a while they added 2 more pins, and then now they could do descenders. And now, of course, we use laser. The VF of an LED is typically around 2 volts. It's not germanium. It's on up there. I mean, it's not germanium or silicone. It's going to be gallium doped with other materials. Rule of thumb, if you don't know the VF of the LED, then you can use 2 volts at around 15 milliamps and you should be safe. But what you should do, if it's available, what should you do? What would that information be at? In the data sheet for the LED. That's what you should use, because this is the way we calculate that series resistor. When operating in a circuit with a voltage greater than the LED's rated VF, a series dropping resistor has to be what is required. LEDs have a very low reverse breakover voltage between 4 and 7 volts, so we usually don't reverse bias these things. If you exceed the breakover voltage of a diode, not a Zener diode, what's going to happen? It's going to burn up, right? What we can do is we can put a regular diode in series with it. And then we can operate it at higher voltage. Y'all understand what I'm saying? Yes or no? So I could come over here and I can have my LED, right? And then I could come over here and put a regular diode in series with it. And of course, we would add 7/10 of a volt to it. But now I might have 1,000 volts up here. As long as the breakover voltage on my regular diode was not over 1,000 volts, then we could run an LED at that voltage, right? And then we forward bias it, then we would choose a resistor right here to drop all the rest of the voltage over to VL. That makes sense? So VRS is equal to DS minus D forward. RS is equal to VRS divided by IL, where IL equals IF maximum. Why don't you divide that? Huh? Oh. These are my formulas. It would be my mistake. So let's say we come over here and we got an LED, and we'll just use the standard. And we'll put a common down here, and I'm going to power it up off of 5 volts. Let me move it down so I can get out of that little graphic up there. And I'm going to power it up over 5 volts. So if I put this thing across 5 volts, if I apply that 5 volts right there, what's going to happen? It's going to burn up before you even look at it because it's over the VF, right? You understand that? Anything above a VF, over VF is considered a short circuit. So if I'm going to power this thing off of 5 volts, then what am I going to have to do? I'm going to have to put a resistor in series with it, right? Okay. And we'll call it RS, kind of like we do because it's a series resistor. So what do we need to do to calculate the size of a resistor? R is equal to what? Okay, it's equal to V. So this is going to be whatever voltage RS has to drop by the forward current of the diode, because that's what we're trying to do. We're trying to get the diode light to turn on, right? That makes sense? So let's come up here and look. Let's use 5 volts. I'm sorry, let's use a 5 volt supply. And then to turn the thing on, we need to have at least 2 volts, but we're not concerned with that now because I've got over that. And we're going to say this is going to be at 15 milliamps. So what size resistor would I use? So how would we use it? So what did you use for the VL? You used 2 volts here, which would leave what, 3 volts there? Okay. What's that? So it'd be 3 volts at 15 milliamps, right? So I don't know what the divide by 2 is in there. Of course, what would I probably do with this? Would I round it down or round it up? This right here is usually, what they use is they give you the maximum current that would flow through there. If you round down, you're going to exceed the maximum current. Just burn it up. Right? You understand what I'm saying? So what would you do with this? You'd use the round it where? Round up. You understand what I'm saying? Yeah, what they give you on the LED, they don't give you, they give you a typical current, but then they give you a maximum current. And the maximum current means if you exceed the maximum current at 2 volts, then what's it going to do? It's going to get hot and do what? Burn it up. So what we do on these guys is we round down. So about a 200 ohm resistor would do. Most of the time you'll see, most people use around a 330. That's pretty standard. 330 or 470. The bigger the resistor, the less, the dimmer the LED is going to be. Right? You understand that? So 330 is a standard size for on a 5-volt supply. Well, basically, you can calculate just about any supply now, right? You understand? I could say, okay, what if I put 100 volts up here? Well, you're going to choose a resistor that's going to drop what? 98 volts at 15 milliamps, and then you're going to round down. And so, I'm sorry, round up. Kind of like the spray that's killing everybody. And then they say Roundup has some type of cancer-causing element in it for people. So I don't know where the divide by 2 came from. What formula is in the formula sheet? The LEDs is the LEDs on there? Well, this is not a complicated task. This is just a series circuit using Kirchhoff's law, right? So if you know the VF of the diode, and by the way, if you notice that sheet, that's one of the things that it gave you over here on the right hand side. It gave you the VF. So if we don't know it, we use 2 volts, and then it gives us the maximum current flow. So 50 milliamps would be good, right? Understand that? Just about every one of them is 20. But you notice as we go through the chart, 2 volts is a pretty good approximation, if you don't have the data sheet. So the lowest that it ever goes down to is 1.5 volts. The highest it ever gets up to is 3.8 volts. So if you use 2 volts, if you don't know 2 volts, then it would be okay. And notice 15 milliamps, every one of these is at what? 20 milliamps. So 15 milliamps is a really good rule of thumb if you don't have the what? If you don't have the data sheet. Are you okay on that? That makes sense? Pretty straightforward. All right. So generic, use if the data sheet is not available, we use a VF of what? 2 volts and an IF of 15 milliamps. And then we usually round up to the next standard, yeah. Because there's not much difference between 15 and 20, right? 7-segment displays, LED displays, we have 2 types. We have what we call common anode and common cathode. And this is done inside. So instead of me bringing out a pin, all these guys are going to do is turn on segments, right? You understand that? So when I bring out, so if I'm doing 7 segments, that would be, if I brought out the anode and the cathode of all these LEDs, that would be 14 pins. Right? If I didn't do a decimal point. Most of your LEDs have got decimal points on it. So if I put a decimal point in there, then that would be 16 pins just for LED for this. So what they do inside the 7-segment displays is they either make the anodes common, so this would be a common anode. Notice in this one, inside the 7-segment, this would be a common cathode. Normally they put 2 anodes on there. You don't have to put both of them. So they put 2 power pins, by the way. And they do that because you can pick up the common on either side. Or the power. Are you okay? That makes sense? So you don't have to hook up both of them. This is in what we call a DIP, which is a dual inline package. Can y'all see these? So what does DIP stand for? And you see why, so it's got 2 rows of pins and they're in line with each other. So they're just called DIPs. What you're looking at is what I gave y'all as a standard size for what we call a 14-pin DIP. But they don't have to use all the pins. Why don't they have to use all the pins? Because we don't need all of them anymore. So the pins, if you look at it from the top, this first pin up here, this would be pin 1. And then you come up through there. If you see a space, you still count it as if there's a pin there, right? You understand that? And the last one down here would be pin 7. Then you come across, straight across, and then the first pin on this side would be pin 8. Then you start counting. If you see a space, you count it like a pin was there, right? Does that make sense? And then you'd go up, and the top pin up here would be pin 14. And this is what we call a 14-pin dip package. Even though there's not 14 pins there, it's got the standard spacing that would allow 14 pins to be there. That makes sense?
So which side? So my question is, which side? Does it matter which side is pin 1?
Yes.
Well, according to your picture there. Okay.
So your decimal point is going to identify the bottom.
Yeah,
Right? Top and bottom.
Yeah, two decimal points.
Well, what we'd have to do then is look it up, because we have the ability to do what they call left-hand decimal points or right-hand decimal points.
But see, you look at your picture there, you only got one decimal. You got two decimals.
Sometimes we have one, sometimes we have two. Sometimes only one of them's hooked up, because they'll have a standard cap that they put on those things, whether they use 2 decimal points or 1 decimal. So I don't think all those are lit up. You can count the number of pins. So if it's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 pins, then both the LEDs are not hooked up. I mean the decimal points are not. I'm sorry. It would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pins, because here's the decimal point right there. So we can look that up or check it with a meter. Notice that on both these, your common is pin 3 and pin 8. Now, old meters could not check LEDs. They didn't put out enough voltage. But most of our new meters will put out, like this guy here, it'll put out 3 volts. So if it puts out 3 volts, up to 3 volts, then I should be able to check an LED with this guy, right? So how would we check an LED if our meter will check them? So that's one thing you need to find out. Is I'm going to come over here and put my negative, I'll pull out my resistor, put my negative toward the cathode. Oops, I need to put it on the diode scale. Oh, y'all can't see it. I don't know if y'all can see this. So this meter, a little LED, you can really see it. I'm gonna try to point this up toward you right here, and I'm gonna forward bias it. Can you see it come on? Let's see it come on. Yeah. So, and it's measuring 1.5 volts, right? And then I'm gonna come over here. Oh, y'all can't see my meter. So this is forward biased, 1.5 volts. The LED comes on, right? And then when I reverse bias it, of course, it should show up. This meter's weird. This meter don't. This is the maximum, but it don't show an overload. But your meter should do what? Show an overload. So we can check LEDs if our meter puts out over 2 volts. Your meter's got to put out over 2 volts on the diode scale, right? And you can actually see this guy here turn on and turn off. That's better. See it? So we could identify which one is common, right? It would take a little while. This is pretty easy, but we could figure that out with our meter. And we could figure out if it's common anode or common cathode. So I might start out with my black lead on the common pin, and then touch it. If I didn't see anything, then I'd swap it over, and I could figure out if it's a common anode or a common cathode. Now, what is the difference between a common anode or a common cathode? It's how you turn them on, right? You understand how you turn them off. So a common cathode, I'm finding my blank sheet of paper. I should put one in there, but it's up here, way back up here. And we'll draw it on one side instead of spread it out. So a common cathode would look like this. And I'm not going to draw the diode symbol because I'm going to draw on the LED symbol. I'm just going to draw them as diodes. It's just a lot faster. And there would be 8 of them in there if we have a decimal point, right? This would be the cathodes. And inside, these would all be tied together. And then they'll bring out 1 or 2 pins right here. Now, what would we connect this to? Well, we would connect this to the minus. Right? You understand that? So what would we turn these things on with? Well, we would turn them on with a voltage, right? If it was over 2 volts, then we would have to put a resistor in each one of these. I'm sorry, my resistors are looking like inductors. Now, a common anode, then we would do exactly the same thing, except what I would do here is I will make it a little easier. I'm gonna leave all my diodes there. Then I'll come up here and just take this side and just make this common. And then I would come out with at least 1 pin, right? And then what we would do, you see some people do this, they'll put 1 resistor right there. But the problem is with 1 resistor, you save money, but the more LEDs you turn on, the dimmer they get, right? So the standard way to do it is to come up here and put a resistor in each one of the cathodes. And here we would turn them on by somehow grounding that, right? You understand? Now, PLCs have no problem with this. In digital, we have special integrated circuits that actually generate an output for us. 7-segment drivers. We have a 7447, which is a common anode driver, and then we have a 7448, which is a common cathode driver. And they would take a binary code, we call it BCD. They'd take a binary code and they would turn on the segment. So if you put the code for a 7 in there, it would turn on the right segments to display a what? 7 for you. It would automatically do that for you. So these guys have been around for a really, really long time. 7-segment display. And that's the way you buy them. So if we would go to a site like Yamaco, and look, they're going to be called CA, CCs are going to be what? Common cathode. CAs are going to be what? Common anode. And then it might have LH. What does LH mean? It means it would have a left-hand decimal point, right? So we do a lot of business with Yamaco Electronics. And then we'll just come up here and search for 7-segment displays. A 7-segment display, common anode, 7-segment display, common RH. What do you think that means? RHDP? Right-hand decimal point, good. 7 segments display, green, 1 digit, right, CC means common cathode, right hand decimal point, so notice they do it different every time. Here's 2, you can get 2. Here's a group of 4, which is very standard. Here's a group of 4. You can go ahead and get a group of 4, right? Does that make sense? Different sizes. They got big sizes. They got little sizes. They got some real big ones, real small ones. It all depends on what you're looking for. Jumbos is what they call them. In fact, let me pause this. We might fire this. I don't remember if it's common anode or common cathode, so I'll figure it out later on. But, so this is a 7 segment display. If I can zoom out. So it's just the segments are made out of just one. This LEDs. And this is the circuit it turns on. These are transistors, guys, that we'll get in toward here. Transistors are they're current valves. It takes a real small current to control a big current, so we can get a current gain out of a transistor. Be careful with the back because they're sharp. So this is really a 7 segment display. So we bought this from Jamico, so they probably got the kit down here somewhere. So now that we understand, okay, so this would be a transducer. They don't cover, they cover displays in your book. Image display terms. You probably heard these a lot, but you didn't understand what they were. So a pixel, have you ever heard of pixel? What is a pixel? It's a pixel element. Actually, it's a square. It used to be dots, but now it's primarily squares. A triad is a group of red, green, and blue colors. And it's on a black background. So basically, to display colors, we got 4 colors we use. We use red, green, blue, and black. But black is the background, right? You understand that? This makes sense? So a pixel is a picture element. It consists of what we call a triad, which is a group of red, green, and blue on a black background. A pixel resolution is the size of the pixel, which determines the sharpness of the picture. Basically, it's the number of pixels that you use. It's the number of triads that you use to generate a pixel. So when you change your resolution, that's what you're doing. You're changing the number of triads that's used to represent a pixel. Everybody okay? Does this make sense? Everybody okay? So I can change my pixel resolution real fast. Well, I'm not going to. But I can just right click here on my screen, right? Go to what? Screen resolution. And then when I come up here, right here, this is my pixels. That's my pixel. So the more pixels I have, the more we're doing. So the smallest a pixel could be would be the size of one triad, right? That makes sense? That's the maximum resolution that your display will do. But then your computer, your video card can combine triads into pixels and make the pixels bigger, right? Which means they take up less memory. So big pixel resolutions, big pixels, they become more grainy. And you see that happen. We call it pixelation, where you take a picture that's taken on your phone, and then you bring it into and then you start expanding it, and you'll start actually seeing the squares. You'll actually see the pixels because you're taking a pixel that was made of this many, and then you're making them bigger, right? We call it pixelation. Sometimes your digital TV will do that. It'll pixelate on you when they start having problems with their video screen. Ever seen blocks pop up there? So this is the pixel size. So this is what my video card supports. It supports all the way from 800 to 600, all the way up to 1366 by 680. The first number is the number of pixels we have across, and then the next one is the number of pixels we have down. So now our displays are in a rectangle, right? So the advantage of running a real low pixel resolution is your screen updates faster, but you can actually, your video gets less resolution. The smaller the pixels, the better the resolution, but the longer it takes the computer to update. And then if you get far back, then the pixels get smaller. When they first came out with projection TVs, the pixels were pretty big. So what did you have to do on those projection TVs to get a really pretty picture? You had to sit way back from them, right? Yeah. But now our pixels, now that we've gone to LCDs, where we can make the pixels really small, then we can get, now these TVs, you can get right up on them now, and they're really, really sharp.
So what's the 4K? Is that the next thing that's going to take over?
Yeah, but you got to understand you have to have a TV that has the ability to do that resolution. Right now we're standard is 1080 by the standard pixel resolution now. And plus, the cameras that they're snapping those things, the pictures with, has to have that resolution too. So
they got to match up.
Yeah. So this is why high definition took so long to come into play. For one thing, we had all these different companies vying for the standard on high definition. And another thing, you had all these broadcast companies that was doing 320, right? Yep. And they would have to update every piece of equipment they had, everything they had, to handle that pixel resolution. So that's why the high and broadcast was even longer than that. Cable adopted it first, right? And then you got to have the TVs that have the ability to do what? Pixels. So I don't know how long supposedly 4K will take to come.
So it's kind of fun about 4K.
Until the broadcast company sees that it's going to be very, very, very beneficial. If y'all remember VHS, Betamax, y'all remember Betamax? Yeah, it was a smaller tape.
Kind of like an 8-track?
Yeah, but it was real small. VHS was these big guys. And so what did we adopt? Well, everybody started buying VHS, and what happened to Betamax? It was gone. So these companies these television companies are not gonna do that until there's a demand for it. It's just like doing 64-bit color. When my eyes can't see 64-bit color. Your eyes can't discern 2 to the 64th different colors, right? You understand? And people will go out there and do that. So 1080 to me is fine. I mean, I don't think going to this higher resolution is going to do any good when you're sitting back on the couch. Now, if you get up there like that, that might make a difference, right? How many of y'all stand with your nose on the TV? So I think it's a waste of time. It's just a selling block. It's just like people go out and buy an iPhone 8 and all they do is go on Facebook, snap pictures. Right? Because they got to have the what? So, and people will do that. So they'll go out and buy these 4K TVs and they'll brag about the resolution and they're still getting what? Unfortunately, it is. So I don't know. I can't tell you. To me, it seems a waste of money to buy them anyway because you wouldn't, sitting on your couch, 15 feet away, you won't be able to tell the difference between what. Huh? Yeah, but it's a waste of money. So we okay here? So we can measure this. If you can't measure it, then what you could do is you could put it in series with your ammeter, right? You understand, and run it. You can see which one's which. A typical photodiode circuit, pretty straightforward, right? Oh, I'm sorry. These are photodiodes. So this is not an LED. These are photodiodes. This is not in the text. So these are the photodiodes. We don't have many of them, so don't. Special purpose diodes whose leakage current is controlled by the watt. The amount of light striking the P-N junction. So these guys operate reverse biased. Everybody understand that? If you forward bias them, they act like a diode, right? You understand? Placing the circuit reverse bias, as the intensity of light goes up, the photodiode's leakage current goes up. These were the first things that we used in light remotes. My uncle was one of the first to get a remote control for his TV. He was always aligned. You have to understand, I came from black and white, so the first TVs I remember was black and white. And then my uncle was the first one to get a color TV. And then he was the first one to get a remote TV. But it was a wired remote, which means what? You had a cable coming out of your TV, and you had a remote control. That's true. You hooked it up, you plugged it into the TV, it had a plug on it. You had a cable, you come up. Then they came out one that generated tones, so it was like a tuning fork. So you'd hit it and it'd strike a tuning fork, and then they'd have a microphone over there on the TV. That was the first wireless. Yeah, you hit a click, kind of like it popped. Once you went across that lever, it would pop and ding, and your TV would pick up the ding and through a microphone. And then we went to, thank God, finally went to what? Yeah, I was one of those that says, you know, when I'm too lazy to get up and change my channel, yeah, then you get kids and you say, go change the channel.
Yeah, I did that a lot of times. Grandma, I tell them to 40 feet, and you had to click the knob.
Yeah.
Boy, she off outside playing.
Oh, she wouldn't get us to call you outside. No, we never did that. And then now we can't live without our watch. So now, when we turn on our TV, we start doing what? Luckily, most TVs still have an on-off on them, but and I still use that. So usually, when they first came out with the remotes that worked off light, they used these photodiodes, which is nothing but a special diode with a lens that light passes through. Sometimes it might have a filter lens on it to prevent certain wavelengths from passing through, right? You understand? Like that one will allow ultra-red to come, ultra-red to come through. As the intensity of light goes up, a photodiode leakage current goes up. And this shows you. So this is the picture for lambda. So this is one symbol. The other symbol is the same symbol, but they draw the arrows pointing in. So we put these guys in reverse bias, and then here we're measuring across the resistor. So as the leakage current goes up, the resistance of the diode goes down, right, which causes the resistor to drop more voltage. Yeah, these point in. Are we okay? This makes sense. Then we have pin diodes. And we'll look to these when we get into transistors. Most of them now use photosynthesis to pick up the light. And these guys are real fast. The pin diode, the photodiodes are fairly slow. And plus, they don't give us much current, right? You understand? We're operating these things in reverse bias, And we're talking about a very low current change. So we'd have to have a really big resistor. A transistor gives us the ability to get a current gain. So that means we can get a lot more current out than we would with a photodiode. So just about all your sensors now, like in this projector up here, is using a phototransistor.
Through beam is that what it's all about?
No, a through the beam is a phototransistor. Just about all our light sensors are phototransistors. We're going to talk about that in a minute. So these are our photoelectric sensors. And man, we got a ton of these on our line over there. So photoelectric means they sense light. They generate light and sense light. Sometimes they're at a wavelength we can't see. Right? But all the ones we have over here are around 600, 660 nanometers, so it's red. Most of ours are red over there. So this is one way we can use these. We could have a light source on one side, which is going to be an LED, right? You understand. Then we shoot this over to a receptor, which is probably it could be a photodiode, but it's highly unlikely now. It'd probably be a photodiode, but a phototransistor, but it does the same thing. It senses the light, right? Okay. And of course, you can see what happens as these boxes move on the conveyor belt. What does it do with the beam? Breaks it. So the output of the sensor would give us an indication every time something moved through it, right? Understand that? Are we okay? So we call this through the beam. These are through the beam